lecture, we will collect all the results that we know, linking the determinant of a matrix, the invertibility of this matrix, and the linear independence of certain vectors. In particular, determinant of a matrix A, invertibility of A, linear independence of rows and columns of A, and finally the rank of A. At first, let A be any matrix. We are not assuming A to be a square matrix. Then the determinant of A is not defined, nor we can talk about invertibility of A, which is defined just for square matrices as well. All we can say are the following statements. One is that the rank of A, by definition, is the maximum number of linearly dependent rows of A. I remind you to remember the maximum number of linearly independent rows, not just the number of linearly independent rows, which is not a well-defined quantity. A rank of A is also equal to maximum number of linearly independent columns of A, and these are part of the definition, if you will, of rank of A. And we have seen these statements in lecture 6.6. And more recently, we have remarked this equality in lecture 7.5, which expresses the rank of A as the maximum order of non-zero minors of A. Let's now assume that A is a square matrix of order n. Then we have the chain of these equivalences. Determinant of A different from 0 is the same as A is A invertible, which in turn is the same as rank of A is maximum, which means rank of A equals to n in this case. And this is one of the most fundamental results of linear algebra. Indeed, I can mention to you the following example. So for instance, I immediately know that the matrices 1, 3, 2, negative 1, this is a 2 by 2 matrix, and this 3 by 3 matrix are invertible without knowing their inverses. In fact, the first matrix has determinant different from 0, or even we can see even more easily that the two columns are not one multiple to the other, therefore they're linearly independent. So if the two columns are linearly independent, then the rank of A is 2, which is maximal. And by this chain of equalities, we see that this is equivalent to the fact that A is invertible without even having found its inverse. The same goes for this 3 by 3 matrix. We can't really see straight away that the column vectors are linearly independent. It is easier in this case to compute the determinant, expanding it along the third column, for example. So the determinant of this matrix is 3 times the determinant of submatrix that we obtain deleting the second row and the third column. And the determinant of this 2 by 2 matrix is clearly non-zero. Therefore, 3 times a non-zero number is different from 0. And so we conclude the determinant of A is different from 0 and A is invertible, without knowing their inverses, as I mentioned before. Let's now prove these equivalences, starting from the implication, the red implication right bound, meaning that determinant different from 0 implies A is invertible. So this follows from the theorem of lecture 8.1, which gave a formula to compute the inverse of A in the case A is different from 0. So in that case, we even have a formula to compute the inverse of A, using the fact that the determinant of A is non-zero. The implication in the opposite direction is a corollary of Binet theorem, which we have stated in lecture 7.3. Remember, Binet theorem states that the determinant of a product of matrices is the product of the determinant of each of the factors. So in this case, we use the Binet theorem in the following chain of equalities. So we start from the identity of these two matrices. So we have the identity matrix on the left equals A minus 1 times A. This is by definition of inverse of A. Applying the determinant to both sides of this equation gives an equality between the two real numbers, determinant of identity matrix and determinant of this product of the two matrices. Therefore, we have 1, which is the determinant of the identity matrix, equals the determinant of A minus 1 times A. And now we apply the Binet theorem that implies, in this case, that the determinant of the product of these two matrices is simply the product of the determinants of the factors. So determinant of A minus 1 times determinant of A. And looking at the right-hand side of this chain of equations and the left-hand side, we see that 1 equals the product of two real numbers. Therefore, each of these two real numbers is non-zero. In particular, the determinant of A is non-zero. Finally, we prove the equivalence of the statements which we have connected with the blue arrows. A is invertible if and only if rank of A is maximal equals to n. Well, for what we have just proved, the statement of A invertible is the same as the determinant of A different from 0, so we can replace the invertibility of A with the determinant of the matrix being non-zero. And proving the equivalence between determinant of A non-zero and rank of A maximal, this just follows from the theorem of lecture 7.5. The statement of that theorem was that the rank of a matrix, not necessarily square matrix, the rank of a matrix equals the maximal order of the non-zero minors of the matrix. In this case, A is a square matrix. Therefore, notice that A itself is one of its square submatrices, is the largest square submatrix that A contains, is A itself. Therefore, if rank of A equals to n, for example, then by that theorem, we know that there is a submatrix of order n in A whose determinant is non-zero, but there is only one submatrix of order n in a square matrix of order n, and that is the matrix itself, so it is A itself. Therefore, necessarily, that must be the submatrix whose determinant is non-zero, so A is the determinant of A is the non-zero minor that whose existence is implied by the theorem of lecture 7.5. So vice versa, if we assume that the determinant of A is different from 0, since again A is a submatrix of itself and it is the square submatrix with the highest order in A itself, then its determinant is a minor of A. And saying the determinant of A is non-zero, it means that in A there is a non-zero minor of order n. Well, but that must be the rank of A, because rank of A cannot be larger than the order of the matrix. So this proves the equivalence between these two statements.